If you've ever felt that graphing with just x and y axes was a little too, well, rectangular for the curvy, beautiful world we actually live in, then you are in the right place. Today, we're going to crack the code of polar curves, a completely different and honestly a much more elegant way to graph some truly amazing shapes. Yeah, and this quote really hits the nail on the head. I mean, forget trying to describe a flower petal with some long, clunky polynomial equation. In the polar world, these incredibly complex shapes can pop out of equations that look stunningly simple. It's like learning a whole new language for describing the world around us. So that's really the big mystery we're going to solve today. How does a little bit of trigonometry, a cosine here, a sine there, suddenly blossom into a rose or a perfect heart shape on a graph? Well, we're going to decode these equations one family of curves at a time. Let's get into it. Okay, first things first, we have to build a solid foundation. And when you're talking about polar coordinates, there is nothing more fundamental than the circle. I mean, these are the absolute building blocks for understanding everything else that's going to follow. And what's so cool here is just how simple this is. The equation r equals a just means, hey, the radius is always a, no matter what the angle is. And boom, you get a perfect circle right at the origin. But watch what happens when we toss in some trig. For r equals a cosine theta, think about it. The radius is biggest when cosine is 1, which happens right on the positive x-axis. And the radius is 0 when cosine is 0, which is along the y-axis. This kind of pulls the whole circle over onto the x-axis. The exact same logic works for sine and the y-axis. So this is our first big clue. The trig function basically tells the shape where to sit. All right, our foundation is built. Now let's move on to something with a little more flair, something a bit more spectacular, the rose curves. I'm telling you, this is where polar coordinates really start to show off. We're about to find out the surprisingly simple little secret behind all those elegant petals. So here's the general blueprint for any rose curve. It looks a lot like our circle equation from before, right? But there's one crucial little addition, that n tucked right inside the cosine or sine. Now the a value out front, that just controls how big the petals are. But n holds the real secret to the entire shape. And this is the key question. Does an n of 3 mean you get 3 petals? Does an n of 4 mean you get 4? I mean, you'd think there's just a simple one-to-one relationship here, but polar coordinates have a really cool little twist in store for us. And here it is, the code is revealed. This is just so cool. If n is an odd number, like 3, 5, or 7, you get exactly that many petals. Simple as that. But, and this is the tricky part, if n is an even number, like 2, 4, or 6, the number of petals doubles. So r equals cosine of 2 theta doesn't give you 2 petals, it gives you 4. That is the one counterintuitive rule you just have to burn into your memory. All right, next up, we've got another really fascinating family of curves called limicons. Now, these things are true shapeshifters, seriously. Depending on the numbers you plug into the equation, you can get everything from a cute little dimpled circle to a shape with this strange and awesome inner loop. And the secret, once again, is all in the numbers. So let's check out the equation. This time, we don't have a multiplier on our theta. Instead, we have these two numbers, a and b, that are being added together. And the entire shape of the limicon is determined by this little tug of war, this relationship between those two values. So what's the control knob here? How do we dial in the exact shape we want? Well, the answer isn't about A by itself or B by itself. Nope, it's all about how they compare to each other. It all comes down to a really simple ratio. And check this out, this chart tells the whole story. It's all about the ratio of A divided by B. If A is smaller than B, so the ratio is less than 1, you get that wild inner loop. If they're exactly equal, you get the famous heart-shaped cardioid. And then, as A gets bigger and bigger compared to B, the shape starts to smooth out. First, it gets a little dimple, and then it becomes pretty much a perfect circle again. It's this beautiful, smooth spectrum of shapes, all controlled by one simple fraction. Let's just pause for a second and appreciate the cardioid. It happens at that perfect balance point where A equals B. The name itself actually comes from the Greek word for heart, and it's easily one of the most recognizable and classic polar curves out there. That sharp little point, we call that a cusp. It always sits right at the origin. So we've decoded circles, we've decoded roses and limicons. Now let's pull all that knowledge together and talk about how to become a real master of the polar code. And that means knowing the common traps people fall into and really understanding the trickiest concepts. Okay, here are the top 3 mistakes people make. First, forgetting that the even end doubles the petals in a rose curve. It is so easy to forget that one. Second, mixing up the orientation. Just remember, cosine is tied to the x-axis, so it opens left or right. Sine is tied to the y-axis, so it opens up or down. But that third point, ignoring negative r values, that's the one that really deserves a closer look.
Okay, so here's the deal. What does a negative radius even mean? If your formula spits out a negative number for r, you don't just stop. What you do is you face the direction of the angle, but then you walk backwards. You plot the point by reflecting it straight through the origin to the other side. And it's this weird walking backwards step that actually traces out that mysterious inner loop on the limesons. It's a direct result of the math creating a feature that would be, frankly, a nightmare to describe with regular old rectangular coordinates.
Okay, I get it. This is all super fascinating from a math perspective, but you might be thinking, does any of this actually matter in the real world? And the answer is, oh, you bet it does. This is not just some abstract exercise. The shapes we've just decoded are fundamental to fields like engineering and physics. Take a look at this. It's called an antenna radiation pattern, and it is a perfect real-world polar graph. In this case, r isn't just distance, it's the strength of a radio signal, and theta, of course, is the direction. This is literally what engineers use to map out how well an antenna is working and in what direction. And what shapes do you think they use? The very ones we just learned. A cardioid pattern is absolutely perfect for something like a directional Wi-Fi antenna because it blasts a strong signal forward and almost nothing backward. In really complex systems like phased array antennas can create these intricate rose curve patterns to target signals with incredible precision. The shapes are exactly the same, the application is just different.
So the next time you see a polar equation, don't just see a formula. See the story it's telling. See the code inside of it. You can now predict if it's going to be a circle, a four-petaled rose, or a heart-shaped cardioid before you even plot a single point. And that ability to recognize the shape first is a huge advantage, especially as you move on to calculus and start doing things like finding the area inside these beautiful curves. You've cracked the code.